Have everyone a nice day. My name is JFReyes, and the topic that I will address is Thevenin equivalent circuits. Thevenin's theorem was developed by the German scientist Hermann von Helmholtz in 1853, but was rediscovered by the French engineer Léon Charles Thevenin in 1883, from whom the theorem took the name. From now on, I will share a PowerPoint with you in order to explain the topic in more detail. The Thevenin theorem states that any linear circuit, no matter its complexity, can be simplified to an equivalent circuit containing only a single voltage source and a series resistance connected to a load. Therefore, if a part of a linear electrical circuit is considered between two terminals A and B, this circuit can be replaced by an equivalent circuit having only a voltage generator in series with a resistance. And when connecting an element between the terminals AB, the voltage and the current that circulates by the terminals are the same in both the real and the equivalent circuit. As we see in the picture, if we have a complex circuit with voltage and current sources and many electrical components, and if we consider a pair of terminals A, B, then the Thevenin equivalent will have only two parameters, a Thevenin voltage in series with a Thevenin resistance. And this circuit will behave in the same way as the actual circuit with respect to terminals A, B in terms of voltage and current. Now, Thevenin equivalent applies only to linear circuits. In a linear circuit, all component equations must be linear, which means that equations do not have exponent or roots. In practical terms, the circuit will be linear if it contains only passive components such as resistors, inductors, and capacitors. Common nonlinear devices include diodes, transistors, and other semiconductor components. They are not linear because they show opposition to electric current changes with voltage and or current inputs. Now, we'll show a basic example of the steps that must be followed to develop a Thevenin equivalent circuit when we have resistors. If we also have inductors and capacitors, the Thevenin approach uses different mathematical entities, as will be shown later. In the step 1, we remove the load and replace it with an open circuit and calculate the Thevenin voltage, which is the voltage across the open circuit. In doing that, we use Kirchhoff and Ohm laws. As we see in the picture, we have a very simple circuit with two direct voltage sources which have opposite signs, 12 volts and 5 volts, two resistors, 3 ohms and 7 ohms, and a load tied to terminals A and B, which is the one we have to remove. So we remove the load, and we have to calculate the Thevenin voltage using the remaining circuit. In this circuit, we see that the net voltage is the difference between 12 volts and 5 volts because they have different sign. Therefore, 12 minus 5 is 7 volts. Then the resistance of the circuit is the combination of 3 ohm and 7 ohm resistance. And those resistance are series resistance. Therefore, the total resistance is 3 plus 7, equals 10 ohms. Then we calculate the current, which is the voltage divided by the resistance. That is 7 volts divided by 10 ohms. Then the result will be 0.7 amperes. Now we can calculate the Thevenin voltage, which is the voltage of the terminal A with respect to terminal B. To do that, we can use the left path or the right path. If we use the left path, that voltage is 12 volts minus the voltage drop across the 3 ohms resistor. That would be 12 minus 0.7 times 3 equals 9.9 volts. If we do that using the right path, the voltage will be 5 volts plus the voltage raised across the 7 ohm resistance because the current is a clockwise current due to the fact that the left voltage source is greater than the right voltage source. And in this case, the Thevenin voltage would be 5 plus 0.7 times 7 equals 9.9 volts, the same as before. And that would be the Thevenin voltage. Now we have to calculate the Thevenin resistance in the step 2. To calculate the Thevenin resistance, all voltage sources are replaced with short circuits and all current sources are replaced with open circuits. In this case, we have voltage sources and therefore short circuits. As we see in the diagram, we eliminated the voltage sources and we put short circuits. Now, the Thevenin resistance is the resistance of the circuit with respect to the terminals AB. And we see that that resistance is the parallel combination between 3 ohms and 7 ohms. So the Thevenin resistance would be 3 times 7 divided by 3 plus 7, which gives us a Thevenin resistance of 2.1 ohms. Now we have the two parameters of the Thevenin equivalent and we can deploy the circuit. The Thevenin equivalent circuit then will have Thevenin voltage of 9.9 volts and a Thevenin resistance of 2.1 ohms. And this circuit will behave exactly the same as the original circuit with respect to terminals A, B. Now, if we also have inductors and capacitors in the circuit, which is the case when we have alternating sinusoidal voltage and current sources, we use the phasor method developed by the German electrical engineer Charles Steinmetz in 1893. This method used the concept of impedance instead of resistance. The impedance reflects the opposition to electric current of an element or circuit. The phasor method is the transformation of the variables from the time space to the phasor space as complex numbers. The phasor transform of the impedance Z for the single electric components are given by the following equations. For the resistor, the impedance is simply the value of the resistance R, which is a real number. For the capacitor, the impedance is -1 divided by J omega C. And for the inductor, the impedance is J omega L, where of course, R is the resistance in ohm, C is the capacitance in faradios, R is the inductance in henrios, omega is the angular frequency of the voltage source in radians per second, and J is the imaginary number square root of -1. Once made the phasor transformation, we can use the same procedure of the previous example throughout the Kirchhoff and Ohm laws to calculate the Thevenin voltage and Thevenin impedance. With sinusoidal voltage and current sources, Thevenin equivalent will have complex expressions. As we see in the pictures, if we have a complex circuit having alternating voltage and current sources, resistance, inductors, capacitors, and a pair of terminals A, B, the Thevenin equivalent will have phasors or complex expression for Thevenin voltage and Thevenin impedance. In this representation, of course, letters C, D, E, and F of Thevenin voltage and Thevenin impedance are real numbers, and J is the imaginary unit. Now, the amplitude of each complex variable, Thevenin voltage and Thevenin impedance, in the Thevenin equivalent can be calculated using the complex component of both variables. And the amplitude in each case would be the square root of the real part square plus the imaginary part square. Now, when the sources are sinusoidal in the time domain, the Thevenin voltage may include a phase angle theta with respect to the input signal. In the time domain, the Thevenin voltage will have a sinusoidal expression, similar to what we have here. In this expression, Vm is the amplitude, omega is the angular frequency, t is the time, and theta is the phase angle. As we show in the next figure, if we have a Thevenin voltage, which is the gross line in this plot, that voltage may have a phase angle with respect to a voltage which is a reference voltage. And that reference voltage normally is a voltage source in the original circuit. Now, the Thevenin voltage phase angle can be calculated using the following expression. Theta equals the inverse of the tangent of the imaginary part divided by the real part of the Thevenin voltage complex number. At the end, I have a couple of comments. First, there is a dual version of the Thevenin equivalent, which is the Norton equivalent. The Norton equivalent also has two parameters, the Norton current source and the Norton impedance in parallel with the current source. And those parameters can be easily calculated from Thevenin equivalent parameters. Second, the Thevenin equivalent is very important in the design of electrical systems because Thevenin impedance should match or should be very similar to the impedance of the load in order to maximize the power transfers between the circuit and the load. In other words, in order to minimize the power losses when we tie the circuit to the load. That is the case, for instance, when we use a power source to charge our mobile phones. This is the end of my presentation. Thank you.